last talk of our conference. And it's a great honor, great pleasure to introduce Professor Milton Lopes from Federal University of Rio de Janeiro, who is going to talk about the energy balance for 2D incompressible fluid flows. Please, Milton.
All right. Thank you, Marcelo. Before I get going, let me just take a moment to thank the organizers for the opportunity to talk to you, but most special, since mine is the last talk, give a very special thanks to the people who put so much work organizing this conference, and very especially Annie, right? So Professor Annie Bronzi did what I regard as a hero's job in organizing this, and it's surprisingly complicated issue of organizing a remote conference. So in the name of all the speakers and the people attending the conference, I'd like to extend to Annie especially and to the other organizers a heartfelt thank you for their work. Okay. So having said that, let me go to the talk itself. So what I'm going to talk about is joint work with Helena Lopes in its totality. And a part of it is also joint work with Alexei Sheskidov and Shvedkoy. Let's see. Frozen. Oh, okay. So the basic problem, the basic underlying problem, is to characterize to give study properties that are specific of weak solutions of the incompressible Euler equations, which happen to be limits of vanishing viscosity. And we would say those which are physically meaningful. Okay, and the motivation is very clear, right? The point is, given the constructions coming from convex integration, there are too many weak solutions. If you use the classical notion of weak solutions for the Euler equations, there are too many, and and it will be natural to seek selection criteria for these weak solutions. And of course, the vanishing viscosity, saying that the solution is a vanishing viscosity limit is a natural selection criterion. But of course, it's a bit hard to put your hands on. Okay, so even if you use that as selection criterion, the question, of course, still is, are those such solutions unique, which is open in many ways, for broadly open. And it'll be interesting to get tools to study these such solutions anyways. So this is the point of asking this question. Okay. Now, of course, you can seek all kinds of properties of vanishing viscosity limits. And in this talk, I'm going to focus specifically on proving conservation of energy, or studying conservation of kinetic energy. And the motivation for that is related to the Onzager conjecture. And I'll get into a little bit more detail in a bit. Okay. So let me start with the Navier-Stokes equations, which I wrote down here, okay, just for form's sake, because I assume everybody knows the equations, but one's supposed to write the PDE you're talking about anyways. And I'm gonna, for this talk, I'm gonna be doing everything I'm gonna be talking about is flows on the periodic torus 0,1 cross 0,1. Okay. Again, for various reasons, this is basically the issues I want to discuss are amply, how do you say, showcased in this particularly simple case. Okay. Now, so let me just go into the Onzager conjecture issue a little bit. So the Onzager conjecture is as stated in a paper by Lars Onsager in 1949. It basically says, or Onsager was basically saying, that incompressible flow with a third derivative, conserves kinetic energy, third derivative or more conserves kinetic energy. So if you want and the point is, Inviscid dissipation is an ingredient, a necessary ingredient for turbulence modeling. So you would expect to have turbulent flows to have a third derivative or less. This is an interesting contrast with Brownian motion, has half a derivative, right? So a third derivative is a bit more regular, yes. No, a bit less regular than Brownian motion, but okay, fine. The point is, in thinking about Brownian motion, you say, okay, but if you expect turbulence, okay, you have to have a flow which has a third derivative or less. Now, that's a physicist statement, and we'll get into it a little bit more in a bit. But let me just say that, okay, so then there is a couple, this becomes a couple of research lines. One trying to show that flows with a third derivative or more are conservative automatically, and to construct examples of flows with a third derivative or less, which exhibit Inviscid dissipation. Okay, so just the exploration of this threshold goes with a little history that I put down in red. Okay, starts with the result by Frisch and Sulem in '75, which says that any weak solutions of the Euler equations with age 5-6 or more than age 5-6 regularity in the Hilbert space hierarchy are automatically conservative. Then a paper by A. Which says that solutions which are L3 in time, C1/3 plus in X are conservative. The refinement of that result by Constantine and TT the same year will say that, or actually you can prove that you're conservative if you L3 in time, B1/3 plus 3 infinity, that's Bezoff space 1/3 derivative, L3 based with secondary index infinity. And the state-of-the-art result would be in this direction would be by Cheskidov, Konstantin, Friedlander, and Schildkoi in 2008, and they show that if you are L3 in time, B1/3, 3, C0, and see there's no 1/3 plus, but actual 1/3 derivative, and so this is a result in the critical space. Okay? You still have conservation of energy. Okay. Now these results apply to 3D flows, which are what is actually interesting. Okay, but all of these results have this peculiarity that you are assuming the solution is in a certain place, but you don't know that the solution is in that place. You don't know existence, or you don't know that if you start in any of these spaces, that the solution stays there. Okay, so this is a hypothesis that you put on the solution to conclude conservation of energy. In 2D, the difference is that you can actually prove that if you assume something about the initial data, you can actually prove that weak solutions emanating from that initial data have, the property that you want, in fact, conservation of energy. And the two results I'd mentioned in that direction, specifically for 2D, is for vorticity in LPP greater than 3/2. Okay. Well, first for vorticity in LPP greater than 3/2 is the result by Duchamp-Robert in 2000. And for the critical case, it's P equals 3/2 is by Cheskidov and Ali. In fact, the same paper that they proved this. This is a consequence of this P equals 3/2 is a consequence of their work. Okay. All of these critical spaces that we're talking about, all this transition here, okay, comes out within it's one scaling. Okay, you go into different classes of spaces, you get different precise different spaces, but the scaling is always the same. Okay, and the scaling is related to something to the good behavior, something called the Reynolds stress, and that's what I'm going to explain next. Okay, so where does this Onsager critical scaling comes from? So here's an idea of a proof of such a result. Okay, so I'm going to do the Euler case. Okay, take a modifier, eta epsilon, convolve the equation with the modifier, call U epsilon the convolved velocity, P epsilon the convolved pressure. So write down an equation for the modified velocity, and that looks like this, the Euler equation with an error term. This error term is what is usually called the Reynolds stress, or some version of the Reynolds stress, U epsilon dot grad U epsilon minus eta epsilon convolved with dot grad U, okay? Some kind of commutator between modifying and the nonlinearity. Now, given that, so once you have that, you have a precise energy balance equation, multiply the equation that you obtain by U, and get what I would call an energy balance equation here, that you want to pass to the limit when epsilon goes to 0 to derive something for the original weak solution that you started. Okay, so send epsilon to 0, and you're gonna see these the terms here conversion to whatever it is that you want. This term, I said weakly converted to 0, but in the prime to 0, but it isn't 0. I wanted to converge to U epsilon minus U. In fact, I wanted to converge to ddt of U squared over 2. This one, I want, it's a divergence term, and I want to show that this thing converges to 0 in the prime. Okay, and I want to study the behavior of the convergence to 0 of this term. So I want these two terms to go to 0. Under which conditions? So the question is, under which conditions this term goes to where it should go, and these two terms go to 0. That way you derive the energy conservation. Okay. So now, if you go hunt for this, okay, you need to require some regularity for you in order to get these terms behaving the way you want. Now, these two, the time derivative of U squared and the nonlinearity, you can pass the limit. I'm not going to show you how, okay? But you actually you have some space to play. All you need to require is that the vorticity to be L6 fits or better than L6 fits. That's enough to show that this thing will go to 0 in the prime, to show that this thing will go to 0 to where you want. But this term is more singular. The term involving the Reynolds stress is more singular. Okay, and to show that this thing will converge strongly L within L1 to 0. Okay, you need P to be 3/2 or better. Okay, so these are 6/5. The criticality for these terms is 6/5, but the criticality for this term is 3/2. And why is that? Okay, so now let me show you just briefly where this 3/2 is coming from. Start with a vorticity in L3/2. Okay, then the velocity is in LP star. Okay, vorticity is in LP, velocity is in L1, is W1P is one derivative better. Now you use the Sobolev embedding, that's in LP star, and P star is 2P over 2 minus P in dimension 2. 2P over 2 minus P is 2 over 3/2 times 2 minus 3/2 to the minus 1, or in other words, 6. Okay, so if omega is in L3/2, use L6 in 2 dimensions. And the term that you sort of bothered here, the U epsilon log grad R epsilon, has the structure of U grad U. So it's U squared grad U. Okay. Now U squared, if I use L6, U squared is L6 times L6, which is an L3. Okay, and grad U is this has the same integrability as vorticity. Okay, the relation between derivatives of velocity and vorticity is a 0-order operator. So if omega is in L3/2, the derivatives of velocity are in L3/2. So you got L6, L6, L3/2. Therefore, L3, L3/2, and these are dual to each other. These are Lebesgue dual to each other. So this is exactly the threshold that makes this term L1. Makes this this is omega equals in L3/2 is exactly what makes this thing integrable. Okay, and that's precisely where so this is precisely the condition. Now once you open things up, it's precisely the condition that will make this thing converge to where it should go. Okay. So at this stage, what I'm going to say, focusing in 2 dimensions, I'm going to say, okay, so vorticity equals 3/2 is Onsager critical. Anything which is less integral, so vorticity LPP less than 3/2 would be Onsager supercritical, and anything for vorticity bigger than 3/2 would be Onsager critical. Vorticity bigger than 3/2 or bigger than or equal to 3/2, we already know the weak solution kinetic energy. By just using this particular idea here as a natural arc. Okay? And so what's left is what happens between P between 1 and 3/2, therefore the Onsager supercritical. Okay, so first observation before going beyond Onsager, going Onsager supercritical, is just to say that this result in some sense is optimal. Okay, and this is an example that we constructed in a paper in 2016. Okay, we say that there exists a divergence free vector field U in B133 infinity intersection W1P. Okay, for any P between 1 and 3/2, such that the limb soup of what I'm calling pi q of x, and pi q of x is defined as SQ of U dot SQ of U dot grad U. Now, this SQ is dyadic truncation, and dyadic truncation is a kind of mollification. So what I'm saying is that this term, pi q of U, has the kind of structure of the U dot grad U of the Reynolds stress. So for this nonlinearity, you got the limb soup on Q going to infinity of this thing different from 0. No, there is no timing. So all I'm saying is that there is a velocity. You can't make point is that you can't. This is non-zero means this is ill-behaved, and you can't expect the thing that you were looking at, the U dot grad U, to be well behaved if this is badly behaved. Okay, so this example shows that in some sense that argument that criticality 3/2 is optimal. Okay, fine. Then what do I have to say more than that? Now we're going to introduce the fact that we want to talk about, we want to discuss solutions which are limits of vanishing viscosity. So let me say that a solution U continuous in time into L2 is physically realizable, which is a weak solution in the standard velocity form, which is cited first. It's a weak solution in the usual sense, and second, there exists some U nu solutions of the Navier-Stokes with viscosity nu positive, with as nu goes to 0, first U nu converges to U weakly, L infinity L2, which is you always have, because you always have at least for a subsequence, because you have conservation of energy. You can extract a subsequence that converges weakly, and you by the energy estimate, and the initial data converges to the initial data for Euler. The initial data for Navier-Stokes converges to the initial data for Euler strongly in L2. So I assume the initial data converges strongly, and I assume the solution, corresponding solution, converge weakly to something which is a weak solution, and that weak solution is what I'm calling physically realized. This is not asking too much in some sense. Okay. So now let me. So the theorem and our theorem from our theorem from 2016 is to say U physically realizable. Use a physically realizable solution. Suppose that the initial vortice is LP for some P greater than 1. Then the corresponding U conserves kinetic energy. So what I'm saying is that if you assume the initial vortice is LPP greater than 1, and therefore through a whole range of supercritical vorticities, still the weak solution that you obtain as limit conserves kinetic energy. Okay. So let me go over the proof briefly with you. Okay. Suppose that omega naught is now p less than 2. Okay, in the case p greater than or equal to 2 is trivial. Is already covered. Omega naught is not and so I'm assuming it's LPP greater than less than 2. It's not L2. Therefore, the L2 norm of approximations of omega naught will blow up. But that's okay. So the vorticity omega, which is omega nu, curl of nu, satisfies the Navier-Stokes equations. Okay, multiply this by omega nu, integrate to get an energy estimate. You get a vorticity. To get an L2 estimate for vorticity, you get this: ddt of omega nu L2 squared equals minus 2 nu grad omega nu L2 squared. Okay. Now start with this energy estimate. Do Gallardo-Nirenberg. Omega nu L2 is less than or equal to grad omega nu L2 to the convenient power 1 minus p over 2 omega nu LP to the p over 2. Then, using this and this, get also no more. Then you can write minus 2 nu grad L2 squared, the dissipation term, as you can estimate it by minus 2 nu and use the Gallardo-Nirenberg. Omega nu L2 to 4 over p minus 2, omega nu LP to the minus 2p over 2 minus p. Moreover, omega nu L2, omega nu LP is less than or equal to omega nu not LP. Okay, this is a maximum principle, vorticity maximum principle for the vorticity equation. So ddt of omega nu L2 squared is less than or equal to minus 2 omega nu L2 to 2 over 2 minus p, omega not nu LP minus 2p over 2 minus p. The L2 norm I can't estimate like that because this is actually going to blow up when t goes, may blow up when t goes to 0. I don't have that kind of control, but this one I have, okay, by hypothesis. So call gamma of t the omega nu L2 squared, and C naught equals this constant here, which is only dependent on initial data. Integrate this differential inequality in delta delta t. No, I can't integrate from 0 to t, as I said, because initially this thing might be infinite. Okay. If you integrate, you get gamma. Oops. If you integrate, you get gamma of t to minus p over 2 minus p minus gamma of delta and minus p over 2 minus p is greater or equal to 2 nu c naught p over 2 minus p minus delta. That's just integrating this inequality. Okay. Now you send delta to 0. This term that has the delta would go to 0, but since the exponent here is negative, we actually go to infinity. So the point is that this thing will go to infinity, but if you exponentiate into a negative power, the whole term is going to 0. So this thing is going to 0. This thing is converging to omega nu L2 squared at time t. And this thing is whatever it is. I send delta to 0, you left with 2 nu c naught t over 2 minus p to the power 2 minus p over p, by the way, this, which is what I put when I put this back up over there. So I got some kind of estimate for the L2 normal vorticity, how it behaves, both in nu and in time, when you play with these constants nu and t. Okay. Let me call this inequality. This is the most important bit of information for the story. Let me call this inequality star. Okay. So to conclude, to move forward, you go back to the energy identity. ddt of u nu L2 squared equals 2 minus 2 nu normal grad u L2 squared. And rewrite now the gradient of u, the L2 norm of the gradient of u is equal to the L2 norm of the vorticity. This is a little, sort of a trivial little exercise. Okay. Once you get to that, integrate in time and use the inequality star. What you get is this: u nu L2 squared minus u naught L2 squared is greater or equal, it's less than or equal to 0. It's greater or equal to minus 2 nu integral from 0 to t of this expression. Okay. Integrate in time, you get this expression, and this is order of nu squared nu 2 p minus 1 over p and that goes to 0 when nu goes to infinity. So the conclusion is this thing converges to this thing, and if you even get a rate, okay, the L2 norm converges to the L2 norm of the initial data for the when nu goes to 0. Moreover, okay, the L2 norm, now this is, I use a little canon, the L2 norm in time of the viscous approximation converges to the solution of the Euler equation in energy. So the energy, there is no, this is a theorem by Dupernamide in 87, says that there is no concentration of energy when P is with vorticity greater than 1. So, and you have that the initial you have a hypothesis that U0 nu L2 converges to U not L2. Therefore, okay, pass to the limit when U goes to 0 using this estimate, you end up showing that the L2 norm of the solution of the Euler equation is conserved. Okay, this is the theorem, the whole story of the theorem. Okay, so fine. So what else can be said? Okay, first observation is that this result has been improved by Lantaler, Mischer, and Pares Pulido, a preprint by 2000 this year. Okay, that shows that there is an equivalence between U nu convergent to U strongly, LT in time, L2 in space, and conservation of energy for weak solutions. And I'm sorry, once you have that conservation of energy, so the theorem that we proved is an immediate corollary of this, because this will be the Dupernamide observation. Okay. Now this theorem, as I said, includes our result as a corollary, but the analysis is quite different, and it relies on the study of something called the L2 based structure functions, which is well motivated by the study of turbulence. Okay, instead of vorticity estimates. Okay, fine. So this is a generalization of what I just showed you with a much more complicated proof. Okay, the case P equals 1 is interesting and wide open. Okay, this is not something we know how to do. Next, so the step that we took forward is to add forcing. Okay, which usually is something somewhat silly. Well, I mean, once you have a theorem for the equation without forcing, the theorem for the equation with forcing shouldn't be too hard. Okay, but at least at some level, this common wisdom fails a bit. So add forcing. So now I'm going to talk about the Euler equation with the forcing, and I want to figure out what kind of conditions on F I have to impose, or on approximation of F nu I have to impose to guarantee that when I send nu to 0, okay, I end up with the energy identity, what is actually the conservation of energy for the Inviscid limit. So PDT of 1/2 integral of U squared equals the integral of FU in the Inviscid limit. Okay, so this identity is what we aim for. Okay, so the problem is find conditions on F so as to obtain the energy identity. And why would we care? Okay, well, first, turbulence requires forcing. Okay, so forcing is, if you want small scales, you have to force the flow. Okay, so actually, this is, from the point of view of applications, it's a very natural thing to want to include. And second, wild solutions can be interpreted as using what Schneermann called ghost forces to produce the weak solutions. So in some sense, is okay. So which ghost forces don't work is sort of what we are aiming at in the background in some sense. Okay, so what kinds of wild solutions what kinds of constructions will not lead to wild solutions in some sense? That's what we're looking at. Okay, so adjust the definition of physically realizable with forcing. So I'm going to say that U continues into L2 and F L1 into L2 give rise to a physically realizable solution with forcing. If one, it's a weak solution. Two, the family of viscous approximations you knew. With forcing F nu, the forcing F nu is in L1, L2. And as nu goes to 0, U nu converges to U weakly, L infinity L2. F nu converges to F weakly, L1, L2. And U nu 0, the initial data, converges strongly in L2. So this is what I mean to be physically real. Just add this condition that the forcing is controlled weakly L1, L2. Okay? And the theorem that we proved is, well, if U is physically realizable in the sense above, and in addition, first, omega naught is LP for P greater than 1. So that we keep. Second, curl of U naught, omega naught nu, converges strongly in LP to omega naught. That's, we had to add, right? Not only we are assuming that omega naught is uniformly bound in LP, but we are assuming that the initial data is converging to the initial vorticity stronger than LP. Okay, and third, and now is the condition on the forcing is that G nu, which is the curl of F nu, okay, is bounded in L1 in time into LP intersection L infinity in time into L2. Okay, then U satisfies the energy balance identity. Okay. That's the condition we found. Now, what do you have to change? What changes between the theorem with and without force? So that's the remainder of the talk. Okay. So first recall that the star, the key estimate, was omega naught L2 squared less than or equal to this expression involving nu and Q powers of P. Okay, and this comes from L2 estimates in vorticity and a Gronwall, a little L2 estimates and a Gronwall in the vorticity equation. Okay, now, or not a Gronwall, but just an integration in time. Okay, fine. So now, the problem is getting this becomes a little more complicated. So with forcing, this estimate star becomes, okay, to prove that the limit when nu goes to 0 plus, and here there's a type, there's a nu missing here. So limit when nu goes to 0 plus, or nu times the integral from 0 to t of omega nu at time s L2 squared, okay, is equal to 0. This is what I want. This is what I want to show, okay, and this will be enough to prove the theorem as I stated in the previous slide. Okay, so this proposition is if you know this proposition, the proof of theorem is the immediate adaptation of the 2016 results. So the point is, once you know that, okay, there isn't. It's not that there is nothing else to do, but there is nothing new to do. Okay, so the whole story is this proposition. As I said, with a type, we need a new here. Okay, so now let me just go over very in a sketch of what gets complicated in the proof of this proposition. Okay, and the problem is, well, you have to sort of cook up a new Gronwall. Okay, so let me call the thing that I want to estimate norm of omega nu in time L2 of the torr squared. Okay, and call this quantity here Z nu of t. Okay, now there exists a pair of constants A and B. The point is that there exists a pair of constants A and B, and I'll show you what the constants are in a bit. Okay, and a power alpha greater than 2, such that the time derivative of this thing is less than or equal to A nu Z nu to the power alpha plus B Z nu to the power of 1/2. Okay. With B equals 0, if it was B equals 0, a simple integration in times gets the estimate star, and therefore gets the limit when nu goes to 0, nu times that as you wish. Okay, so if B equals 0, you're back at the non-force system. So the whole problem is B. And as you can see, okay, so I have this EDT less than or equal to some function of Z. Okay, and this function of Z is dominated by alpha. Alpha is greater than 2, so it's dominated by the negative power, but has a small factor in front. And then it has the square root bothering. The point is that how to play these two things out, kind of a singular perturbation problem, but for a very simple ODE. Okay, how to play these two things out and see and get precisely what the power of nu that you get, so that you can get this estimate over here. Okay. So the proof of step 1 is just an L2 estimate on the vorticity equation. The constants A and B are given by here the constants A and B that you get. Okay. I'm not going to go over this, but that's what it is. Put in the vorticity equation, do the L2 estimate on vorticity, and that's what pops out. Okay, with these particular constants here. Okay, so you need a Gromov to be able to do this. So the next step is note that this guy omega naught nu L2 squared is left, which is z nu naught, goes to infinity and nu goes to 0 because omega naught is not L2. And omega naught nu L2 squared may be infinite or finite. I'm not saying that the approximation of doing the initial data, okay, is L2 or not. If it's just a modification, it certainly is L2, but it doesn't have to be. Okay? In fact, it could be just keep omega naught always the same, okay, fix omega naught, and therefore, you know, then the L2 norm is infinite. And I don't want to make any further assumptions on this. Okay, because I want the condition of being, I want the condition of being physically realizable to be as natural as possible. Okay, and therefore I don't want to impose any conditions on how you approximate omega naught. Okay. Now, so this omega naught nu L2 squared may be infinite or finite, but the z nu of delta is finite by parabolic regularity. If the initial data is LP, the solution of the Navier-Stokes equations is smooth for every positive time. In particular, it's L2. Okay, so by parabolic regularity, this guy's fine. Okay, so the second step is look at the solution of. So we have a differential inequality that we want to normalize. So look at the solution of the ODE. M prime equals minus a nu m plus b square root of m. For t greater than the delta, m of delta equals z nu of delta. Okay, give it the same data at time t equals delta, and use the same ODE, but now with the equality. Then the step 2 says we prove that z nu is bounded between 0 and m nu of t. Okay, for every time between delta and a fixed time horizon peak t. Okay, now the proof of this is probably the heart of the story. And again, it's an elementary fact. The proof is phi nu is strictly concave. This function that it is the flux, the little flux of this ODE is strictly concave. Minus a nu r to the alpha b square root of r behaves like this. If it's strictly concave, in particular, the tangents are above the graph. If the tangents are above the graph, I'm starting with m prime equals phi of m, z prime is less than or equal to z of m, and they are equal at time t equals delta. Phi of z is less than or equal to phi of m plus phi prime of m, z minus m. So as I said, all this means is that the tangent is above the graph, and the consequence of being concave. Okay, and as a consequence, okay, now phi of z, as I said, phi of z is greater or equal to z prime. Phi of m is equal to m prime. So you put these two together, you say that z minus m prime is less than or equal to phi prime nu of m, z minus m. Whatever this is, once you normalize this thing and you assume that they are equal at time t equals delta, then they are equal forever by Gromov. Okay, and therefore, if they are equal forever, by Gromov, this implies that z minus m is less than or equal to 0. And that's what we want, which is this. Okay, so this is this little thing here is the key. So, everything becomes study the solutions. Study the solutions of this ODE. Now I need a precise estimates on what the solutions of this ODE looks like, because I can estimate what I want using this M. And then, it goes, introduce the equilibrium, studying a one-dimensional ODE, introduce the equilibrium, the point where, this point where the flow is zero, separate the cases where this M of t is below equilibrium, above the equilibrium, and in fact, we end up the analysis in 3 cases. The z nu of 0 can be greater than 1. Remember, this can even be infinite. Less than 1, equal to 1, and greater than 1, this lim sup over the 0 r nu of r nu star. This is the damn thing here. Okay, the first case is easy. Okay, the first case, the 2 first cases are very easy, because once you start smaller, you stay smaller forever, and therefore you can estimate z itself by the r nu star, and that's enough to show what you want, that the limit of nu times the integral of z nu star is 0. Okay, and the other case is where the other case is the bomb, is where things get complicated, and to get that, you need to solve the ODE. Okay, and to solve the ODE, you introduce an antiderivative, a specific antiderivative of this quantity, d rho over phi nu rho. Prove things about this function, which is strictly decreasing with an inverse, with a well-defined inverse. It has limits when r goes to infinity and r goes to the end point of the story. Okay, and the proof of these claims is just calculus, literally playing with calculus 1. Okay, it follows that phi nu is a diffeomorphism from this interval r nu star to plus infinity to the interval 0 infinity. Then the solution m dot of phi of m, z of delta equals z mk of delta is, and then you get a formula for the solution involving this phi, which is the inverse of phi t minus delta plus phi of the initial data. Okay, the step 4 is to use this formula plus a bunch of calculations to conclude. Once you get that, okay, again the problem is reduced to patient chasing the constants to be able to conclude. Okay, so the key points in the story: you need an adaptive Gronwall and associated to an inequality of the forms z dot less than or equal to phi of z, which would imply an estimate for z of t. And this adaptive Gronwall is the key point is that phi is concave and decreasing, actually. Okay, it's not just estimates that you need for the story, but precise asymptotics in the singular perturbation parameter nu, and that's what complicates things. And that's one of the things that complicates the argument. Okay, so, and that's all there is to it. Observations characterizing viscous limits. Now, some final observations. Characterizing viscous limits of conservation of integral norms of vorticity is another line of research that's associated to this problem, to the original problem. Okay, this is well explored with a very different and rather deep set of tools. And if you're interested in characterizing solutions for which the norms of vorticity, the LP norms of vorticity are conserved, look recent papers by Ciampa, Kripa, and Spirito, 2021. Another result on this direction is Kripa, Nobili, Size, and Spirito, 2017, and Nussensweig, Lopes, and Wiedemann, 2021. Okay, so this is, as I said, these are this is a very smart, very interesting bit of work, which I just don't have time to get into. And some open problems, right? First, extend the result that we obtained with forcing to the Lantaler, Mishra, and Palais-Pulido context, the one with the structure functions. Okay, look at the case p equals 1, which right now I don't know. I have no idea how to do. This first one can probably be done. Okay. Characterize energy conservation of weak limits of Euler alpha or order desingularizations. This is related to recent work by Gotoda. Okay. And and the fourth is sort of go after examples, find examples of anomalous dissipation through irregular forcing more explicitly, violating the conditions we put in here. Okay, so I guess this is it. Thank you.
Okay, thank you, Milton. Are there questions? So I think anyone can unmute your microphone if there is some questions.
I can see Gabriela has a question.
Gabriela, please ask.
No, I'm just copying.
Okay.
I have no questions.
So Milton, I think, okay,
I have
sorry.
a quick question. Can any of this be extended to other active transport equation?
Yeah, it's there is. I didn't put this in as an open problem, but yes, absolutely. A lot of this would naturally. I mean, of course, you get different results, but a lot of this will actually, as long as you have some kind of meaningful energy balance to talk about. Okay, because you got to the active scalar equation, then you need another equation for what would be the velocity, and then you talk about the L2 normal of velocity conservation. Normally, for active equations, the stuff that has vorticity conservation, so the stuff by Ciampa, Kripa, Spirito, and company, that's more naturally extendable to active scalar equations. It's a little less, but it's still there, especially if you assume you got some kind of Hamiltonian structure on the equation, then it's quite easy to see where the energy goes, okay, in the story.
So are there other questions, comments? So Milton, I have maybe a very naive questions. Are physical reliable solution unique?
We don't know that. In fact,
Okay.
it'd be surprising. You see,
even in 2D?
Even in 2D. There is a way in which this theorem is maybe this theorem, and in fact, I should go back to this theorem. Okay, you saying physically realizable, we define physically realizable, okay, by saying that the U nu is converging U weakly, but this whole definition should actually be saying that there exists a subsequence of new case satisfying these conditions. We weren't quite as careful as it should be, okay? Because you don't expect, so you expect that depending on the subsequence you take, you get a different weak solution, and that wouldn't be a surprise even for 2D Navier-Stokes at this level of regularity that we're talking about. Okay, so it's still but this is open. Okay? I'm saying this wouldn't be surprising, but this is open. Nobody knows if you.
Does the energy conservation does not has some implication that
you have uniqueness? No, and it will be it will be a very big result if you can show that in fact that the physically realizable solutions of this sense are unique. So once the nu has to convert always to the same limit. Okay. But to this theorem and the other one should have been stated for a subsequence, assuming that different subsequences could get you different weak limits.
Okay, thank you. So are there any other questions? So I think there is no more questions.